Great. So in the last class, or in the last two classes, in fact, we have been looking at the Titanic dataset. And our purpose here is to do something called as data pre-processing. That is making the data ready so that we can take it to the next phase, which is machine learning. Okay. So there are a few key items or key elements to keep in mind. First key element is our machine learning model cannot accept missing values. So we have to deal with missing values. And by when I say deal with missing values is either get rid of them by removing the rows or columns, or fill it with meaningful data. So in our example, we saw few ways of doing that. We saw that age was a major missing column. It had around 20% of the data missing. And the way we populated that data is we used something called as title from the name, which helped us extract categories like Mr., Miss, Mrs., Master, and others. And looking at the median, or I think mean of those ages, we were able to populate the missing values for age. Further, we saw that age, by looking at the plot of age, we found that individual ages probably don't matter as much. And what matters more is the distribution of ages. So we found high level concepts like young, adult, mid-age, child, senior, and so on. And we divided our age column into these values. Okay, so I think this is where we had finished. No, in fact, we had even gone ahead and we had done something called as one hot encoding. So we replaced first age to these categorical values of numbers, which now represent higher level quantities. We had also seen embarked, and let me go down. Yes, we did something called as one hot encoding for embarked. That is, we saw that embarked here has categorical values like S, C, and Q. And since this is a nominal data, when I say nominal data, it means that there is no order in between S, C, and Q. Then we would want to replace them with binary variables. And we did so by using something called as one hot encoding. Let me again revise what that is for you. So here we see the embarked column takes values S, C, and Q. Instead of this one column, we create three columns: embarked S, embarked C, and embarked Q. And whenever we have an S here, what we will do is for embarked S, we will put 1, and for the other two columns, we'll keep 0. Whenever we have a C in the original embarked column, we will put an embarked under embarked C, we will put a 1, and other two columns will keep 0. So in fact, what we do by this method is, by this method, we are now able to represent these categorical variables S, C, Q into three columns, which are taking only Boolean values 0 and 1. It is called one hot encoding because in one of the rows, only in one of the columns you will find a 1, and all the other columns you'll find 0. Okay. So we saw that, of course, we don't need to do this manually, and doing this manually is a huge task. In fact, we don't even need to write some special code for it. All we need to do is you will call the inbuilt methods within pandas, and one of those methods is something called as get dummies. Okay, so when we do pd.getDummies, you provide the data set to it, you provide the columns that you will create from embarked, what is the prefix you want. So since I use EMB as a prefix, I give the same prefix here as an example. And I say, which columns do I need to do get dummies for? I say, okay, I want to do get dummies for this column called as embarked. So when I execute this, I look at the train head. Now I see that the original column of embarked is missing in my new train. And instead of this embarked, I have three columns, EMBC, embarked C, embarked Q, and embarked S. And we see that it has populated with the right values. Okay. So I believe this is where we had last finished our discussion. Let me take it ahead, where we now analyze the next column, which is the column fair. First, we verify, do we have any missing values? And we see, okay, we have one missing value. Okay, so we said to fill this missing value, since this is only one, we could easily take the mean of all the fair values and populate it. But the other more what do you say, a more logical option is to fill with the mean of the passenger class. We know that passenger class is correlated with fare, as passenger class 1 is costly tickets, passenger class 3 are cheap tickets. What we can do is we can fill this missing value with the mean of that passenger class. So let me change this to mean, and we are writing a very simple command for both train and test. We are doing a fill NA. So fill NA will fill the missing value, and it asks what is the value that you want to fill with. So you say we want to fill with this part of the value, which is basically saying, let me take my train data, group it by passenger class, look at the fare column, and find its mean. So even before doing that, we could do a small test so that we can see what does this fare look like. Okay. So when I execute this, I see that, okay, so let me, here, since we want to analyze, I will do it for both these columns, P class. Okay, so what I want is group by passenger class, and for each passenger class, I want to see what is the fare. Okay. Okay, I'm doing something wrong. Let me just first let me do a count. I don't have to group by fare. Okay. Yes. So okay, right. So the mean for these is this way. So we'll say that passenger class 1, the mean ticket is 84.15. And for passenger class 2, the mean ticket is 20. And the passenger class 3, the mean ticket is 13.6. So when you want to find a mean, we don't need to do a transform and then pass the mean function. We could do it this way. So I'll change this here as well. I will say fill the missing values with simply the mean here, and I'll do it for both train and test. Okay. So by this simple strategy, we can fill the missing values. So wherever we have a missing value, we will go to the corresponding passenger class, and we'll see what is the passenger class. If the passenger class is 1, we will replace by 84.15. If the passenger class is 2, we'll replace by 20. And if the passenger class is 3, we'll replace by 13. So once we do it for both train and test, now we are also interested to see how the fare is distributed over the survived and the dead category. So I'll go simply and plot it here. So again, I see that there's a huge difference. That is for passenger class, for fare, uh, maybe less than here 20, or less than here around 30 or 40. We can see that less than that value, mostly people did not survive, and more than 40, we see that people have survived. So again, this was expected because we had seen earlier that there was a huge correlation uh, between the passenger class and the people who survived or died. So keeping that in mind, I divide my data into, again, multiple parts, fare 0, 1, 2, and 3. That is anyone less than 17, one group, from 17 to 30, one group, from 30 to 100, one group, and then from greater than 100, another group. After doing that, we are left with fare, which is again now categorical. Okay. Let's look at Kevin. We had seen earlier a huge what do you say, missing values in Kevin. So we'll quickly do train.isNull. Okay, sorry, dot sum, and we see Kevin has 687 missing values. That is, out of the 891 values, we have 681 missing values. And which is a huge percentage. Okay, it's a huge percentage. So when there is a huge percentage like this as missing values, there actually is left no option with us. We should not try to populate this, because even if you try to populate, we are trying to populate with such a huge amount of artificial data. With that in mind, we will simply drop the columns of K. So if we do drop Kevin for train and test, we get rid of it. And now we are left with this much. We will look at one more feature, family size. So you see, we have two features here, sibling, spouse, and parent, children. And what I think is maybe we can combine these two features into a common feature called as family size, where we add how many members are there for that passenger, how many family members are there on board of Titanic. Okay, so the way we calculate that is we add the train sibling spouse with the parent children and that one because of the person that we are counting for. Okay, so when we do it that way, we can see that now we have an additional column called as family size, and we can see the plot of family size between, or the KDE plot of family size between survived and dead. And we say, okay, let us, there are huge values going from 0 to 11. Let us change them, or let us write some code for them. That is, if there is a family size of 1, we will call it 0. If the family size of 2, we'll call it 0.4. Family size of 3, we'll call it 0.8, and so on. And then we have some mapping between the family size between train and test. Post that, this is what we are left with. We have then taken care of sibling spouse. We have taken care of parent children. Okay, why I'm adding 1 during the sum of family size? I'm adding 1 to count the person that we are calculating for. So passenger 0, his family size is, he has 1 sibling, 0 parent children, and his family size becomes 2. Why? Because he has 1 sibling and counting himself, his family size becomes 2. Okay, so this one additional 1 I'm adding for the person who is on board. Okay. Nonetheless, I realize even if you don't add this, it does not make a lot of difference, because ultimately your data is going to be what we say, it's going to be mapped to a different scale. And even here, 1 we are mapping to 0. So if you add it or not doesn't matter, because it's a constant value. You see, maybe this is an interesting point to talk about. When we talk about data science here, and when we talk about the values that we have for different columns, we are more interested in the variance of the data rather than the absolute values of the data. Okay, what I mean is, if my variation is between 5 and 10, I'm interested in this region. I can move this 5 to 10 between 0 to 5, or between minus 2.5 to plus 2.5. It will not make any difference to my machine learning algorithm. Okay, we are trying to capture the variance between the data. So when I look at a +1, and if I do a +1 to all of the data points, then this +1 is basically meaningless. It is not adding value to my model. Okay, nonetheless, we do things like this just to have some level of sanity in the choices that we make. But in terms of the machine learning algorithm, it has absolutely no difference between whether adding this +1 or not. Okay, so I hope we keep things like this in mind, and think how the algorithm will try to interpret our decisions in terms of what we are making it. Okay, let me go ahead and we do a family mapping. Post family mapping, this is what we have as family size. Now, since we have used already sibling, spouse, and parent children, we can get rid of them. Additionally, we have something called as the ticket number. And we can get rid of the ticket number as well, because again, it is just like an identification, just like the name is not as useful. Similarly, the ticket number may not be useful. So I simply drop these three features, that is ticket, sibling, spouse, and parent children. And when we do that, finally, we have finished our data pre-processing. And you look at our data right now, there are 891 rows and 9 columns. And if you look at this data, we can make a few, we can at least make a few notes what is expected out of our phase of data pre-processing. So if I have to quickly summarize, what is expected out of data pre-processing is, first, that we don't have any missing values. Our model will not do good with missing values. Okay, it will fetch out an error. So first, no missing values. Second, it should have no objects, that is no strings. We will convert everything to numbers, because models can deal with numbers very nicely. They can add it, subtract it, manipulate it, find probability for, find greater than, less than, so on, only with numbers. So we convert all of our data to numbers. Okay. Thirdly, we look at if the numbers are confusing for our model or not. So if the numbers are confusing, that is individual values don't matter as much and groups matter, then we would want to take those individual values and bin them. Okay, so we did this for age and fair, where we binned our data. Okay, so that is another thing that we do in data preprocessing. One more thing we do with data preprocessing is we see if we have a categorical variable, and if that categorical variable has ordinal relationship or nominal relationship. So when we looked at embarked, we had C, S, and Q. We saw that they have nominal relationship. That means that there is no hierarchy, there is no ordinality within the data. And since there is no hierarchy or ordinality, we converted that into one hot encoding. Okay. So these are the common things that we would want to do with our data. Of course, data preprocessing has many other things. We can play around with many more things. But on a standard data science problem, these are the first things that you will look for. Okay. Deal with missing values, convert strings to numbers, see if there is an order between the numbers, if the individual numbers matter or not. If they don't matter, do binning. If they matter, then leave it as it is. Uh, uh, Additionally, if we have categorical data, we have to see if we want to do label encoding or we want to do one hot encoding. In this example, we saw one hot encoding where we converted categorical variable to individual columns. Okay, there's something called as label encoding also, which we have not seen so far. But I hope, but yeah, I know for sure that in the examples to come in the future, we'll be seeing that. So we'll add that value as well. Okay. So these are common things we do. Once we do all of that, you see how clean our data is. They are not there. Most of them are within the same range. So we will not have a problem with feature scaling. All of the values look very well. So now we can move to the next step, which is taking this data and feeding it to a machine learning model so that we can extract meaningful insight out of our model. So we did this for train. Similarly, we did this for test as well. Okay. We will move to our phase of machine learning. For that, let me share my iPad screen and we'll take it from there. Okay. I hope you can see my screen. Let me, okay, exit. Yes. So we'll start with machine learning. And within machine learning, we have two major categories. We have something called as supervised learning, and we've got something called as unsupervised learning. For our discussion, we'll focus on supervised learning. And even within supervised learning, we have multiple categories. Let me write for you. So here we have supervised learning, and we divide it into two parts: classification and regression. Okay, and we'll look into what these are. We are going to spend the next few classes within this area of supervised learning. So this just informing that I know supervised learning takes some time to get the concepts right, to get the different algorithms right, and once we deal with at least 3 or 4 algorithms and we have some basic idea of how supervised learning works, then we will go back to our Titanic data set, and the pre-processed, the data that we have processed, we will try to classify it so that we can see for the test data how we can predict the values of people who have survived or not survived. Okay. So an introduction to machine learning. We know that humans, we learn from experience, right? That is, as we experiment with different things, as we, let's say a child is learning to walk, the child will fall multiple times, and in every process of falling, the child will learn how to fall, how does it feel like, what I can do to avoid it. So they will start moving their hands and legs separately. They'll start crawling, and slowly from crawling, they'll move to walking on their 2 legs, just balancing. And slowly over a period of time, now the concept of walking becomes so strong that the child can now run, jump, play. I realize this because I have a small baby, and she's just 1 year and 8 months now. And very recently, I saw in the last few months, last I think 8 to 9 months, how she went from crawling to walking, jumping, and now dancing as well. So we humans, we learn from experience, right? Additionally, humans also learn from instruction. That is, now in this case, when you guys are learning data science, I am acting as an instructor. That is, I'm instructing or I'm exposing you to ideas, and your mind is trying to capture that, and you are learning something. Okay, so there are different modes where humans learn, whereas when we look for machines, sorry, I don't know, I think I got disconnected. Can you hear me now? Okay, great. Yeah, I'm not sure what happened. Nonetheless, let me go ahead. So we said I was talking about machines learn from data. Okay, the problem statement is, what are they learning? So our problem statement is that the machines are learning a target function. Okay, our machines are trying to learn a target function that can be used to predict the values of a discrete class attribute. Okay, we are trying to learn the target function that can be used for future prediction. Okay, in this case, I'm saying I want to predict discrete class attributes because I'm focusing on something called as a problem statement called as classification. But even before we go there, let me try to show this using a small diagram, what I mean and what to do. Okay, so if I look at this box, okay, and to this box I am giving some inputs. Okay, inputs like x1, x2, x3, and my output box is giving me an answer called as y. Okay, so I have some system, and what this system is representing that when I feed in certain features to it, I try to predict what is the output answer. Okay, so if I compare this to our Titanic data set, we are feeding in things like age, fair, family size, and so on. We have multiple features that we feed in, and what we are interested is, we are interested to get out the answer of, will the person survive or not survive. Okay, and the task of machine learning is, when I have loads of data. Okay, so when I have multiple rows and columns of these data, when I feed this data into this, I also know what is my target variable. Okay, so for each data point, I know what is my answer, and if I know what is my input and I know what is my answer, basically I know here input and output. What I'm trying to estimate using the machine learning algorithm is, how is this working? Okay, we are trying to find out what is the pattern inside this model. Okay, and this is what we call as a target function. So when I say as my problem statement, that is my problem statement is to learn a target function that can be used to predict the values of a discrete class attribute. Okay. Once I have learned the target function, now what I can interestingly do is I can use this target function to predict for new data. So later on, so this is my train set. Similar to this, I have a test set. Okay. My test set looks like this. So if I copy and I paste it here, I say for my test set, I have the inputs, but I do not have the outputs. Okay, I have the inputs, but I don't have the outputs. But what I can do is the model that I have learned from the trained data, using this data, I have learned a model. I can now use this model to predict for answers for this model. So I take this input, pass it to my model, and I will get my answers back. Okay, and this answers is very useful for me. Why? Because now from what I knew earlier, I have learned something that can be used for predicting future things. Okay, so just imagine the applications here. Okay, so there can be several applications, and I will show you a few examples of how this kind of a strategy can be useful. Okay, let's look at one example where we have a hospital emergency room in consideration. So we have a hospital, and as soon as a patient comes to the hospital, we have to decide whether this patient goes to the ICU or not. Okay, so this problem is an interesting problem because every major hospital will have an ICU, an intensive care unit, and there are limited number of seats. Okay, so an hospital occupancy of maybe let's say I have 250 beds on the hospital, then my ICU would be roughly maybe 10 to 15 people, not more than that. Okay, so since I have so few beds in the ICU, additionally the ICU is very costly. So to keep patients in the ICU, it costs money to the hospital, then thereby it costs money to the patient as well. And we need to ensure that only emergency situations, that is people who are critical, will go to the ICU. We need to know at least some level of metric who should be sent to the ICU and who should not be sent. So generally, as soon as you go to the hospital emergency room, there will be a doctor there 24/7, and they will measure certain inputs, and based on their experience, they will look at the condition of the patient, and they will make a quick judgment call. That is, that person needs to go to the ICU or not. Now, if I want to solve this problem using a machine learning solution, the way I would go about is first we need to collect data. Okay, so for every patient that comes in, and we have a doctor there who decides whether they go to the emergency room or not. We will see on basis of what is the doctor deciding whether someone goes to the emergency room. Is he checking visually? Is he checking if they are looking okay or not? Is he checking their pulse rate, their heartbeat, their blood pressure, their weight, height, gender, age, and so many things. Okay, so the doctor will be measuring so many parameters, and based on which he will make a call. Now, the doctor basically, even without understanding, what he is doing is he is linking these input functions to an output variable, identifying whether a person goes to ICU or not. Okay, and this target function, this judgment of whether someone goes or not, is based on his years of experience. Okay, so the doctor has studied under many professors over many years and understood what are the basis of deciding this thing, and he or she probably has lots of experience in the hospital to see how their seniors have distributed cases and emergency or not. And based on all of this accumulated data and accumulated experience, the doctor is able to figure out. The machine learning algorithm now has to do the task of taking these same input variables and trying to learn a model that can predict if someone has to go to an emergency room or not. And in the initial few phases, we would probably not put the algorithm at run alone. We would keep the algorithm as a supervisory case with our doctor, and the algorithm will probably give only suggestions. And over a period of time, we will see what is the accuracy of those suggestions. And since hospital emergency room is a very critical case, you would see that over a period of time, as our algorithm gains a lot of experience in terms of data, we try to feed data from one hospital, two hospitals, 10 hospitals, maybe hundreds of hospitals within the city, abroad, internationally. And once we collect all of this data, okay, we would say that our machine learning algorithm has now become so smart that for 100% time of the cases, it is able to predict whether someone needs to go to the emergency room or not. Okay, so this is the kind of thing that we would want to do. We would first train our model with known or supervised data so that it learns what is this underlying pattern. And once it learns this underlying pattern in quite detail, and we are happy with the level of accuracy that we have, then we can take unseen data for which the model has not seen data, and for new test cases, we can use this learned target function so that we can find out what is the prediction variable. Okay. I hope you have understood this example. Another example would mean something like a credit card application. So when you apply for a credit card, the company will see several things. The bank will see several things like, do you have a job or not? What is your age? What is your past experience? What is your education? Do you have a house? Do you have liabilities? And based on that, they would either approve or reject your credit card application. Traditionally, this would happen using a banker. A banker with years of experience will find out or will inform whether someone gets a credit card application, whether someone gets a credit card or not. But nowadays, we have automated processes where we have machine learning algorithms that make these decisions. Once you feed in the data, it will look over years of past experience, and based on that, quickly give an output. And thereby, you see nowadays, getting credit cards have become so simple because we have algorithms which can analyze very quickly if someone will clear the application or not, and we can use that, or we can leverage that information to make predictions for unknown or unseen cases. Okay. Now this, what we talked about was examples of supervised learning. So it's called supervised learning because our training data has the target variable. Okay, whenever our training data has the target variable, then we can use methods of supervised learning. When our training data does not have the target variable, okay, this target variable is not available, we have only input data, then we talk about different level of algorithms called as unsupervised learning. Okay, in this both cases, when we talk about hospital emergency room and credit card application, we are looking at a problem statement called as classification. In classification, our output variable or our target variable, our target class, has fixed number of outputs, has discrete number of outputs. In both the cases we saw, we have two outputs, okay, binary outputs, yes or no. Okay, hospital emergency room, we say that should the patient go to emergency room or not. So again, binary. Credit card application, binary, you get the credit card or you don't get the credit card. Titanic case is also binary, where we say the passenger has survived or not survived. You can have other kinds of classifications like, let's say I give you the image of an animal and we have to predict if that animal is a dog, cat, horse, or goat. And that would again be a classification problem where we are having 4 target variables. So 1 target variable with 4 classes. So when we have such limited kind of options, we talk about an algorithm called as classification algorithms. Okay. Let me go ahead and let me show you some more information or some more introduction regarding machine learning. Okay. So here we generally talk about in terms of data. What we have is we have a set of data records. We also call them examples or instances or cases. And that data can have multiple attributes. So attributes are features or columns that we have. Okay. So these are very common terms that we use. I use them. So I understand that I'm not consistent in my usage. I'm using different terms all the time. Maybe let me quickly show you what I mean. So for this data that we saw here, the number of rows that we have, we call them several things. Okay, we can call our rows. Okay, we can call them as rows. We can call them as samples. We can call them as data points. You can call them as inputs or instances. So all of these are just similar terms for talking about the same idea. Okay, we are talking about these rows. Okay, then when we look at these columns, we can call these columns multiple things. Okay, let me write some of them down. We can call them columns. We can call them features. We can call them attributes. We can call them predictor variables, and so on. Okay, so these are common terms used for these columns. Okay, and you'll find that even when you read literature, people use different terms. So it is in your advantage to know what these terms are and get familiar with them. Finally, when we look at this thing, the target variable, again, this target variable is also called multiple things. So let me write that. As I just said, they are called as target variable. It's also called as target class. It is also called as response variable. It is also called as dependent variable. And since this is dependent variable, here we have one more option called as independent variables. And these are common names used for this target variable. That is our prediction. Oh, they're also called the prediction. So, okay. So multiple terms to be aware of. Let me come here. So here, when we talk about data, what we mean is data is the rows that I showed here. There are multiple examples, instances, or cases, and they're described by multiple attributes or features or columns. Okay, and each class, that is each example, is labeled with a predefined class. Class is the target variable that we talked about. Okay, so this is for machine learning examples. This is what we mean by our data, and our goal, as I talked about earlier, is to learn a model, in our case a classification model, from the data that can be used to predict the classes of new future test cases and instances. So from our data, we'll try to learn something from our about our target class, so that in the future we can use that target function to estimate for unknown or unseen cases. Okay. Let me go ahead. A very simple example. I will not spend a lot of time on this example. Here I have multiple rows. This is a credit card problem. I have columns like age, does the person have a job or not, do they own a house or not, credit rating, and this is a target class. And what the task is to use this data to learn a function regarding how someone is given a credit card or not. Okay, and after learning the function, we want to predict for an unknown case, for an unseen case. So for an unseen case, after you learn the model, I ask the question: if the person is middle-aged and they have a job, they do not have a house, and their credit rating is fair, what is the class? Do we give them a credit card or not? Okay, so that is the kind of question we need to answer after using this data to learn the model. Okay, and this task we call it as machine learning. Okay. Now, as I said earlier, machine learning is further divided into supervised or unsupervised. Supervised and unsupervised are determined based on whether we have a target class or not. Okay, if you have a target class, we go into this category of supervised. If you do not have a target class, we go into this category of unsupervised. We further see supervised is also of two types. You see here that if I have the data and I want to put them in different buckets, in this case 1, 2, 3, 4, 5 different buckets, we can see that I have 5 target variables that I want to predict. Sorry, 1 target variable with 5 classes that I want to predict. So this becomes a classification problem. Okay, I want to classify my sample into one of these points. Other example is this: when I have this as my input. So here I'm showing 1 input and the Y as my output, 1 output. Now you can see I have several different options of inputs and outputs. Okay, if I want to count, if I just want to try counting at least, I can see that I have this one value for output Y, this one value for output Y, this one value for output 5, this one value for output 5. In fact, if I take each of these data points, I will find that I will have unique values of output 5. That means I have many different values. And even after having many different values, I know that if the input is somewhere here, or the input is somewhere here, or somewhere in between, the output would be a new value compared to the input value we have. Okay? We may have never encountered that output before. And in this kind of problem, we see that we do not have fixed number of output values. We do not have fixed number of output values. We have actually infinite number of output values. When that is the case, we call such kind of machine learning problems as regression. Okay, we call them as the regression. And what it basically means that my target variable y can take infinite values. Okay, my target variable y can take infinite values. Those values may follow a pattern, those values may follow a range and so on, but they can take infinite values. Okay, and that is what we mean by regression problem. So quickly summarizing, supervised, two major problems, classification and regression. Unsupervised, we have again two major classes. Okay, one is called as clustering, the other is called as anomaly detection or outlier detection. Of course, this is not an exhaustive list. There are many more categories that you can find, but these are major categories. We will not talk a lot about unsupervised. Okay, let me go ahead. Okay, so how does our algorithm learn, or what is the procedure? Okay, so the standard procedure for our algorithm is we talk about three kinds of data. Okay? We talk about something called as the training data, the validation data, and the testing data. Okay, right now I'm just giving an introduction of what this is, and later in the course I will explain in detail the advantage of train, validation, and test, and how we divide them, how we do cross validation, and so on. But now, for the first time, I'm talking about training, validation, and testing. We take our data and we divide it into these three groups, and these three groups play different roles by learning the model. Okay, so our learning process looks like this. We take our training data and we will use the training data to train a machine learning algorithm. Okay, once we train the machine learning algorithm, what we get is we get something called as a model. Okay, we use that model to predict, or we use that model using some validation data. We take that validation data for which we know the answers. Okay, we know the answers for this validation data, but we try to use our model to predict the output here. Once our model gives out a prediction, since we know the answer, we can evaluate whether our model predicted good or our model predicted bad. Okay, based on what it did, based on whether it predicted good or bad, we will go back and we will modify the model again. Okay, we will take either we'll take a different model, or we'll make changes in the same model so that now it operates differently and so on. And once we do that, we again take the training data, train the model, and so on. And we keep doing this till we have some kind of evaluation metric which we are happy with. Okay, we say that okay, after training our model over multiple cases and multiple iterations, now we have an accuracy of 95%. Okay, so you are happy with 95% and you stop. So that is what we do with our data. And once we have, in this process, since we are still modifying the model, we will say that we are in the process of validation. Once we have come out with a model that we are happy with, and we say that, okay, let me do a final test to see if that model will perform good or bad in the deployment environment. That is the phase when we go into the testing case. Okay, and in the testing case, we will take our unseen data for which our model does not know the answer. We know the answer, but the model does not know the answer, and we will give that as input and see what the model will give us output. And our hope and our idea is that this output model, that this metric that we'll have with the testing data will be a measure of how our model will behave in the real scenario. Okay, so that is in short the learning process, and in short the division of our data. And of course, when we go to more detailed example, I will explain on this concept a little more. Okay, there is one more idea that we call as an assumption, And the assumption is this, that the distribution of training examples is identical to the distribution of test examples. In fact, I will also add one more part. It is identical to test plus validation. Okay. So our hope or the assumption is this, that our training data is a good sample of our testing and validation data. Okay. So you want the same data to train that or the same kind of data to train that our models will be used to test against. Okay. I cannot teach you data science and then test you for big data analytics. Okay. Or I cannot teach you maths and test you for history. Okay. So similarly, even for a machine learning algorithm, our training and testing data, our distribution should look similar. Okay. Now this is easily said, hardly it is implemented, because in many cases you will come across that the training data looks something, and when you actually go to deploy your model and test your model, you'll find that your testing data looks different than our training data. It is having a different model. Okay. So here we have probably done the introduction of machine learning. The first algorithm that we look at is K nearest neighbors classifier. We have some 5 minutes of time. Let me try to see how much of K neighbors we are able to complete. And wherever we stop, we will, in the next class, again, I will continue from K nearest neighbors classifier. Okay. So K nearest neighbors classifier is one of the most simplest models of machine learning that we have. Okay, it is a very simple model of machine learning, and it is generally we call it in its short form as KNN. Okay, and KNN stands for K nearest neighbors classifier. Okay, and this is a classification algorithm. So when I say it's a classification algorithm, that means that my target variable has discrete class variation. So my target variable has fixed number of discrete values. Okay. The statement of KNN is something like this. The statement is this: if you are similar to your neighbors, then you are one of them. Okay, a very simple idea. If you are similar to your neighbors, then you are one of them. Okay. Now K nearest neighbors, or KNN, it basically searches through the entire training data set for the K most similar instances, and the data with the most similar instances is finally returned as a prediction. Okay, so let me probably show you a quick example. Okay, so let's say I have my data distributed this way. I have these examples. Okay, so let me ask you a very quick questions. Okay, I have here data that I have plotted on 2 axes, and can you tell me how many features do we have for this data? What are the number of features that we have for this data? 2. Excellent. Okay, so we have 2 features. One feature is plotted on the x-axis. One feature is plotted on the y-axis. Can you tell me how many classes do we have for this data? Again, the answer is 2. We have 2 classes, the red class and the green class. Okay. What K-neighbors classifier says is, if I have an unknown data, okay. So let's say I have an unknown data here. This is black. I'm representing using this black data. In fact, let me do a highlight on this. So this is the yellow highlighted black data is my unknown data. Okay. What KNN says is, if I want to predict what is the answer for this unknown data, I will simply look at its neighbors. Okay. So in this case, let me look at 3 neighbors. What are the 3 neighbors for this data points? I'll say my 3 neighbors are this one, and this one. So I look at my 3 neighbors and I'll find out what is the class of those neighbors. So the class of these 3 neighbors are red. So what is the majority of the class of these 3 neighbors? We'll say the majority of the class is red. And because this is red, I will label this data point as red as well. Okay. So such a very simple algorithm. Okay. Let me look at a data point here. If I look at a data point here, I say the 3 neighbors will be green. And so I will label this data as green. Okay. Let me now come to the difficult question. That is, if I put a data point here, what do we do? So we'll say, okay, let me find the 3 neighbors here. So in this case, I will say let my neighbors are 1, 2, and 3. Okay. Since my 3 neighbors, 2 are red and 1 is green, I will say that this is also red. Okay. So that is basically the concept of k nearest neighbors. Okay. We will take our data and we'll find our neighbors, and based on our neighbors, we'll predict for the unknown scenario. Very interesting question. If there are equal neighbors, then what will we classify? So if there are equal neighbors, you are left with the option that you can classify anything, right? You can either take it green or you can take it red. But I would say if I have equal neighbors, so in this case, when I have 2 classes, what I will do is I will never take k as an even number. K is the number of neighbors that you will see. Okay. If my k is 2 and 1 is red and 1 is green, then I will be stuck with the problem of which one to choose. But if I take my k as odd numbers always, okay, 3, 5, 7, 9, 11, if I just take odd number of neighbors, then I can always be sure that I will have a majority sometime. Okay, I will never have an equality case. So since I will never have an equality case, my problem becomes a bit more simpler to solve. Okay. Nonetheless, when we have big number of data sets, it is difficult to come up with a value of k where we will say that never we will find an unequal situation. In those cases, you could always go for any one of them. You can randomly choose between red or green, and that would be the prediction of our k nearest neighbors. Okay, we'll stop here for now. There are many more things that I need to talk about k nearest neighbors, but we will continue our discussion in the next class. Okay. Thank you so much. I will stop sharing. Okay, Neerja ma'am, I'll exit now. We'll meet tomorrow. Okay. Thank you so much for joining. Take care. Bye-bye.